Good afternoon. So today's lecture is signal analysis and dynamic response. I will be covering a few points from unit pulse and unit step to step response and frequency response. But for today, perhaps we can only finish the first 3 points. Let's review the unit pulse definition. Here you can see the signal E1 equal to 1 when K equal to 0. Otherwise, the signal is 0. It can be also denoted as delta of K. Therefore, we have the Z transform like this by the definition. Okay, the sum from 0 to infinity of the function of K times Z to the minus K. Because K equal to delta K is non-zero only when K is 0. So finally we have the Z transform as 1. Okay, for unit pulse. Then for the unit step, definition of unit step. Okay, this is not unit pulse but unit step. A signal E2 equal to 1 when K is positive, otherwise K is 0. And the notation of unit step is like this. So most of the time I use this notation. Okay. And here is how we can transform it into Z domain using the definition. Okay, the sum K taken from 0 to infinity, that's unit step function, and times Z to the minus K. And then we have a series expansion, and then we can have the convergent form if the absolute value Z taken like this, greater than 1. So the series is converged and we have the closed form to be this one for unit step. And let's see the location of the pole of this Z transform of the unit step. So poles means you set the denominator to be 0. So this equal to 0, which means Z equal to 1. Here is 1. This so-called has unit radius. Okay, 1. So Z can be complex number. This is imaginary axis. This is real axis. But in this case, Z is just 1, which is real. So location of the pole Z equal to 1 is here. Okay. And the original function unit step E2 of K is this one. So from K taken from 0 to infinity, the function equal to 1. Okay, and K is integer number, and otherwise the function equal to 0, like here. Okay. Now let's see the exponential term. And the one-sided exponential in time. So one-sided means if you draw the exponential curve, it to be like this. So it starts from 1 here. So I mean from the minus infinity, it just 0 like this, and then it jump to here, and it has exponential term to be like this. This is for the case where R has absolute value less than 1, right? And Yeah, so this is supposed to be E3 of k. And we can also rewrite this form to be all of k, and it's just normal exponential function, but then we type the step function. The step function will suppress this part to be 0. Okay? And now we get the Z transform of this E3 by using the definition formulation. And we take only the value of Z such that the series is converged. So we can have closed form. And now you can see here the poles which is found from setting denominator to be 0, right? So the pole here, Z equal to R itself. Okay. So you can see the pole reflect the function itself. If you have pole R, then you have the signal in the time domain or k domain with the R as a base of the exponents. Okay, R is the base. That's why we say when the pole has absolute value less than 1, then you have converged system, right? Because if R less than 1, when the exponent grow, the overall value decrease to 0, right? And here is the graphical representation. One here is about location of the poles. Let's say if Z equal to R, so R is here, okay? And then we have the exponential function in the k domain to be converged like this, okay? Because R is within the unit circle, okay? Right. So this is to show you the relationship between the location of the pole, location of the pole with respect to the unit circle, okay, has relationship with the response and the time domain or the k domain. And the last one, the general sinusoid. Here E4 equals to, if you look at this carefully, you can have actually this term is just cosine, right? This term is just cosine k that I, right? So you have exponents here as the amplitude of the cosine itself. Okay. Then let's find Z transform and find the location of the poles. Okay. Actually, from this one, you can draw the signal in the k domain, like here, when you choose R less than 1. I mean absolute value less than 1. For example, if R equal to 0.7, so you have amplitude of cosine decay, right? The amplitude decay is like this. Yeah, amplitude decay. Yeah. So in here you will have even smaller oscillation, right? Because the amplitude decay. This is all, the red one is all to the k. Now let's see the location of the poles by taking the Z transform of this function. Now let's just take Z transform of this term only. Just R to the k and e to the, this one should be should fall down here, not at the exponent, right? I think it's better to change it now, not to make it confused. Yeah. And then full screen, and then the duplicate screen, and then just take this one. Let me verify this one. Okay. Again. Yeah. So let's see only this term, exponents or k and e to the j k theta. Now apply the definition of the transform, and then we can have a series expansion where the base of the exponential is this term. So we can find the value of z such that this series converges, so that we have closed form like this, and then we can easily find the poles of this z transform. Okay, so the pole here is just r times e to the j theta. Okay, because e to the j theta has absolute value 1. You call it absolute value, or you can call it norm. Okay, e to the j theta has norm 1. So it means r itself is the norm of the whole complex number. So you have poles as complex number. So for this one, for just this term, you have pole like this. Then you have this term. Okay. You will have poles. Okay, let me write poles. The first one is this one, e to the j theta, and pole for the second one will be r e to the minus j theta, right? So it means you have complex conjugate. Okay, you have poles as complex conjugate, and anyway, absolute value of this complex is just less than 1, because just r. And we take value r less than 1, for example, here. So you can see the relationship between these two. Correspondence, not quite a relationship, but correspondence. Like you can say, well, if you have poles, you have a complex number of pole, and it has norm less than 1, which means within the unit circle, within the unit circle, then you have oscillation, but at the same time it decay, right? Oscillation at the same time it decay smaller and smaller like this. Okay. Because the decay is from the exponential, that is decay like this, right? So this is the final answer of the transform of the original function E4. And then once you have these two terms, and then you add them up, and you get the final result. Okay. So here is the mapping from the location this is the mapping of a second order system, mapping from the parameter of a standard form in continuous time to the z domain. Okay. Now I mentioned continuous time and standard form. Let's recall it. The standard form transfer function has this form, okay, omega n square over s square plus 2 times zeta omega n s plus omega n square. So this transfer function of the standard form of transfer function of second order system in continuous time. Okay. So when we choose the right value of zeta and omega n, the right means we choose positive value zeta positive, omega n also positive. Then you have converged response or stable response, right? Why? Because for the transfer function you have the poles, the pole that you set this to 0, and then you find s equal to blah 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 blah. That s is this one, poles from the continuous time. Okay, minus zeta omega n plus minus omega n square root of zeta square minus 1, and this term can be real number and can be complex number, depends on the value of zeta. Okay, if zeta is positive and less than 1, so this term is negative, and if it less than 1, then this term become complex, and this complex has negative real part. Okay, because it always had negative real part, then the system converge. Okay? As long as you choose zeta positive, omega n positive, the system always converge. That's why when you transform it into Z domain, you can see that it's always within the unit circle. This is unit circle. Okay, unit circle, and it's symmetric actually, but I don't need to show the other part, because when you try to find roots of polynomial, and if the roots are complex number, they are always complex conjugate, pair by pair, right? So it means if you have one root here, you must have another root. Okay, let's say if you have one root here, you must have another root here, conjugate. So what does this graph explain? Okay, let me show you the curve, how this graph represent. But first, how to get this graph? Okay, well, you can map from this to the Z domain. This is Z domain by using this relationship, Z equal to e to the ts, and you have s equal to this. Okay, and because here we only study the case where zeta is less than or equal to 1. Okay, you can see zeta from 0.1, 0.2 up to 1 only, which means we consider the case that this term is complex number. Okay, so you have exponential of complex number. What you can get from here? It's still complex number, right? Yeah. So this is the complex number, and this complex number has amplitude. What is the amplitude of this complex number? I can rewrite it as e to the minus zeta omega and t, and then time e to the plus minus omega t, and then time j, I put j complex number here, and then square root of 1 minus zeta square, because we only consider zeta less than 1. So 1 minus zeta is always positive, but this one is inverse sign of this. The inverse sign of this under the square root become this complex. Okay, so you can see here the amplitude. Yeah, this is a purely complex number, and then this term we have like amplitude of this complex number, this whole complex number, right? This term is the amplitude. So this term can be less than 1 or can be looked. Alright, this term is always less than 1. Why? Because zeta is positive, omega n is positive, t is positive. Then e, because e is greater than 1 and it has exponent negative, right? It has negative exponent. So this term always less than 1. That's why you can map, you see the map everything, okay, from the S domain to the Z domain is within the unit circle. So this curve represent constant value of omega n. Well, here in the graph we use omega 0, so omega 0 here means a specific omega, but actually this one here you can see omega n as general. Okay, so let's call it omega n. So represent the omega n constant. For example, here omega n equal to pi over 20t, and then this one for this, I think, and then this one for this, okay, and then this one, oh look, sorry, I think I made, actually this one is this one is 1 over 1 pi over phi t, this curve. If you choose omega and constant and you change zeta 0.1, 0.2, 0.3 and so on, you will get this point, this point, this point, this point, this point, this point, okay, this point. Understand? This is how you map from continuous time to discrete time, from S domain to Z domain. And if you choose constant zeta, let's say zeta equals 0.9, then you have this curve, zeta equals 0.9, and then if you choose omega n equal to 3 over 10, 3 pi over 10t, then you get this point. This is the location of pole, pole for the Z. And this is one complex number. This is a conjugate, maybe around here. Okay, you have you can draw a symmetric like this. Okay. Yeah. Like I said, all complex number found from polynomial are complex conjugate pair by pair. So if you have one complex number as a pole here, then you have another complex number as a pole here. Okay. Any questions so far? Let's say, well, if I choose zeta 0.5 and I choose omega n 7 pi over 10, where is the location of the pole for the z domain? Okay, zeta equal to 0.5, which is this one. Okay, this curve, and then omega n equal to 7 pi over 10, which is this curve. So you have the intersection here. Okay, this is one pole and another pole just symmetric with respect to real axis. All right.
So the other pole is the symmetry of this triangle.
Yeah, symmetric with respect to this real axis.
So what will would be is it still the phi is from 0.1 to 1%?
What value?
The phi value.
Omega n is just omega n like this, and you have another curve which is symmetry to this one, and you have this curve also symmetry, so you have another pole here. And this curve represents the same value of omega n, and this curve, which is symmetry with this curve, also represent the same value of zeta equal to 0.5. Okay. Any more question? Let's see some properties. Settling time of 1%. Well, for all less or greater than 1, no need to say anything about specification, because the signal just grow, right? So if it grow, there's no such a thing as settling time or rise time, because it just rise all the time. For r equal to 1, which is constant amplitude, 1, it means you have this is r, absolute r, supposed to be absolute r. Yeah, so if absolute r equal to 1, then you have there's no something specifying r is complex number. Anyway, it compared to the real number only, then suppose r is real number. So if r equal to 1, which is constant, and at the at here, actually here, okay, because this is a real axis and this is imaginary axis. One here, then we have constant amplitude signal. Why? You can review this unit step. Unit step. Pole here, right? Pole here at 1, and then you have constant amplitude like this. And if r less than 1, and if the closer r is to 0, the shorter the settling time. So if r less than 1, and if it close to 0, 0 is here. So if r close to 0, then the shorter the settling time, which means the response rise from 10% to 90% at very short time. That's what we call settling time, rise time. And here it's about settling time. Also for the settling time, if let's say if the response like this, okay, this is slow rise time and slow settling time of 1% around here, and this is no, I should not say slow or fast, because we say here short or long. So for this one, it has long rise time and settling time, because settling time is around here. But for this one, settling time is around here, so it's shorter, right? Shorter. Any questions so far? Okay. So the last one, if r equal to 0, or itself is 0, then the transition of finite duration. So actually, if you have 1 over z, actually this one is just unit delay. Or we can say the transient just at finite duration. Here let's see the relationship between radius and the response duration. Duration here is using number in 1, 2, 3, 4 instead. I mean the integer number, because k taken from 0, 1. Okay, we just call k belongs to r plus, okay, real number. Oh, sorry, n. N. Natural number. So look here, if the radius, pole radius r is close to 1, which means around here, then the response duration or the settling time is long, okay? Because r power k dies slowly, not fast, okay? Because r is close to 1. If r equal to 1, the exponent just keep 1, right? Just stay at 1. But if it's much smaller than 1, for example 0.4, and then this one die faster, okay, so here for this one it dies slow, for this one it dies faster, okay. Right. Okay, let's take a look at this. A response of second order system. Well, so here let's say we try to find the number of samples that complete one cycle. One cycle, let's say from peak value, the upper peak value, to another upper peak value, or we can say the maxima okay, relative maxima or local maxima. From this one is easy to find. This is one maximum, this is another maximum. So from here to here, like we want to know how many samples, okay? Because the oscillation come from trigonometric function, okay, for example cosine function, then in order to find the number of samples, we use this this condition. Well, yeah, let's look this one again. Let me draw. For this curve we have like r to the k and then cosine that k theta or theta k. So because this one make the system decay, the response decay. Oops. Make the response decay. Then it's a little bit hard to find the cycle of the peak value. For example, the peak value is here, and then another peak value here. Okay. And so this the number of sample here depends on the value of theta itself. Why? Because to have the condition that the peak value at so the peak value of this decay curve is at the peak value of the trigonometric function cosine. So if the trigonometric function cosine here at the peak, and then this one also at the peak, okay, and we want to find cosine value at one point, and then we want to find the sample at which cosine has the same value. So let's say we plus the sample by n to the k, right? We add n to the k, and we still have the same value of cosine, which means if from peak here and then we add n sample, we get the peak here. If at the peak here we get add n sample, then we get the peak here. Or at this value we add n sample, we get the value here, like that. But if you look at the peak value, peak value is easier to visualize, right? Because if cosine is at peak value, cosine type exponential that decay still at the peak value, right? So to have this equality, you need to have cosine theta k plus theta n, right? To be like what? Cosine of theta k plus 2 pi. Because if you have like this, you can have still equal to cosine theta k. That's why we can set up n actually equal to n times theta. N times theta actually equal to 2 pi. So we have n equal to 2 pi over theta. From here we can easily calculate the number of n. Okay, how many samples that you have complete one cycle if you ignore the exponential term and you only consider the cosine, the trigonometric term. And so like here you have r less than 1, so you have exponential decay and theta equal to pi over 4 and r equal to 0.7, just less than 1 already. and then you can find number of sample n. You just count it like 1, 2, 3, 4, 5, 6, 7. And in this case r equal to 1, so there's no exponential decay, amplitude is constant, so this is pure trigonometric function. Okay, and then you can count the number of sample. If theta equal to pi over no, theta equal to pi over 4, then n equal to in this case n equal to 2 pi divided by 2 pi divided by pi over 4, so equal to 8 sample. Okay, 1, 2, 3, 4, 5, 6, 7, 8, like that. Okay, from this peak to this peak you just add 7 sample. Okay, 1, 2, 3, 4, 5, 6, 7, 8. For all greater than 1, then you have exponentially increasing envelope, so this one just grow bigger and bigger, and in that case it's not interesting to analyze. The last of this lecture, you can see the response, the visualization of response with respect to location of the poles. If poles are inside the unit circle, then they are all stable. Okay, like this one inside the unit, this is unit circle 1. Okay. So this one in unit circle you can see stable. This one also inside the big circle, the unit circle, then it's stable. Okay, stable. This one also stable, stable, stable. Here, here is also stable. But if the pole located on the circle, for this one you have a alternate oscillation, right? Oscillation each sample. Okay, oscillation by each sample. But if you have on the circle but a real number and positive here, okay, a real number and a positive which is 1, then you just have constant like this. Okay, and if you have on the circle here and circle here, so actually you have what? You have the real part as less than 1, right? And well, because the real part represents the amplitude of the complex number, and then because this one not inside the circle but on the circle, so it is oscillation. Yeah, it oscillates like this. Okay, oscillate at the unique value of amplitude. And if the location of the pole is on the imaginary axis and still on the circle, then you have oscillation like this. So you also drop to 0 like this, and then to the negative, and then repeat. Different from this one where you don't have at the 0 value. Okay, it just bound between one. I'll say, do we have negative value? If because r is negative. If r is negative, let's say r is negative and -1, right? -1 to the k, so it can be -1, 1, -1, 1, right? So this mean 1 and minus 1 and change all the time. Alright, and the last one, the location outside this unit circle, and it's on the imaginary axis, so you have oscillation grow like this. Okay, just grow to be unstable or to be diverge. Yeah, I think I explained everything, so I don't need to repeat by reading each one of these. Okay, any question? Okay, if no, then let's take a break about 5 minutes. So we're gonna continue at 6 past 2.